So the pipe diameter, capital D, is 30 centimeters. Also, you can see it in the photo. And small d is 15 centimeter. And the atmospheric pressure is 100 kilopascal. What is the maximum allowable discharge before cavitation occurs at the throat of the venturimeter if capital H is 5 meter? Okay, first of all, why cavitation might happen at the throat of the venturimeter? Basically, the throat of venturimeter is over here. The reason that cavitation can happen over there, and there's a potential for cavitation over there, is that D, or diameter of the pipe over there, is very small. This means that velocity is very high. And when velocity is high, pressure is small. So if the flow rate is higher than a maximum allowable, then your velocity is going to be super high, your pressure is going to drop below vapor pressure, and cavitation happens. So in order to find maximum flow rate, or Qmax, I need to find maximum velocity. And maximum velocity happens when pressure at point 2, I'm going to call this point 2, section 2, okay, over here, is equal to vapor pressure, which has been converted to gauge pressure. Okay, so that's the verge of cavitation. If pressure at section 2 is equal to vapor pressure, then your system is on the verge of cavitation, and that has the maximum flow rate and maximum velocity. Perfect. Now, in order to actually solve this problem, I'm going to write down the energy equation between the surface. I'm going to call it section 1 and section 2. And so I'm going to write down the energy equation first. And here is energy equation. The problem statement has not given us any information about head loss, so we are assuming that there is no head loss. That's why I have not included any head loss into the energy equation. I am going to consider the datum to be exactly the center line of the pipe over here. So this is the datum. Now let's see if we can simplify this equation further. First of all, Z2 would be 0 because it's right at the datum. Z1 is equal to 5. Pressure 1 is going to be 0. Atmospheric, that's the surface of water, and velocity is 0 as well because it's a large reservoir. Now, I can simplify this equation or reorganize this equation and write it 5 is equal to P2 divided by gamma plus velocity at 2 to the power 2 divided by 2g. Okay, now remember that we want our P2 to be equal to vapor pressure gauge. Now, we have the temperature of water given to us 20 degrees Celsius in the photo, and we have the atmospheric pressure. So we know that P of atmosphere is equal to 100 kilopascal. So at 20 degrees Celsius, and based on table A5 of your textbook, you can find that vapor pressure, absolute vapor pressure, is equal to 2340 Pascal, or 2.34 kilopascal. Perfect. So now, in order to calculate from these two, in order to calculate vapor pressure gauge, I need to have vapor pressure absolute minus atmospheric pressure. So my P2, which is equal to vapor pressure gauge, is equal to 2340 Pascal minus 100,000 Pascal, which would be equal to negative 97,660 Pascal. Okay, now I'm going to put this value for P2 into my energy equation and find out velocity at section 2. So reorganizing this equation, velocity at section 2 to the power 2 divided by 2g will be equal to 5 meters plus 97,660 Pascal divided by 9,790 Newton cubic meters. And then from this I can calculate velocity to the power 2 divided by 2g to be 14.97 meters. And as a result of that, velocity at the throat of Venturi meter is equal to 17.1 meters per second. And this is the max velocity. Okay, so now in order to find max Q, I just need to calculate velocity at the throat times area of the throat, which is 17.1 times area of the throat is pi over 4 times diameter to the power 2. As a result of that, Q is equal to cubic meters per second. Okay, and this is the maximum flow rate, maximum allowable flow rate. In other words, any flow rate equal or greater than this flow rate will generate cavitation at the throat of the Venturi meter. So whenever you're designing such a system, you need to make sure that the flow rate in your pipe is smaller than this maximum flow rate.